Today we're going to learn about the mean value theorem. So the mean value theorem is a theorem that connects the average rate of change over a certain interval with the instantaneous rate of change. And we use this theorem often in real life. An example of it is looking at average speed. So for example, if your average speed is 60 miles per hour on your drive on Route 66, does that mean you had to drive 60 miles per hour at some point on that drive? If you think about what average means, it means at some point we went less than 60 miles per hour on that drive, and at another point we went more than 60 miles per hour on the drive. Since when you drive, your speed limit has to hit every speed between your lowest speed to your highest speed, at some point you would have had to gone 60 miles per hour, since technically the function is continuous. And that's what the mean value theorem says. So the formal definition of the mean value theorem is that if f of x is continuous at every point on a closed interval and differentiable every point on the interior or on an open interval, there are at least one point c in between a and b, and c is an x value, at which f prime of c is equal to f of b minus f of a all over b minus a. Now remember, f prime of c means the derivative at x equals c, and f of b minus f of a all divided by b minus a means the average rate of change between x equals a and x equals b. So what the mean value theorem is saying that the average rate of change must equal the instantaneous rate of change at some point on the interval, as long as the function is continuous over the closed interval and differentiable over that open interval. Graphically, f prime of c means that it's the slope of the tangent line. And this, f of b minus f of a all over f b minus a, remember, is the slope of the secant line. So graphically, this theorem is saying that the slope of the tangent line must equal the slope of the secant line at some point on an interval AB, as long as it's continuous and differentiable. So here's the definition graphically. It says the secant line through the endpoint of the interval must be parallel to a tangent line at some point on the interval. And they're parallel because two lines that have the same slope have to be parallel. That's the definition of parallel lines. So we want to figure out why a function has to be continuous and differentiable in order for the mean value theorem to work. So if we look on that worksheet I gave you on Monday, this is number 1 on it, and this says they graph this function, and we're looking at the interval 3, 7. And it says draw the secant line and the tangent line. So I already drew the secant line, which is the line that goes through the two endpoints on the interval. And then I found a line parallel to it, and I found it's approximately at this point. So this would be my value of c that I'm looking at, which is approximately like 5.3, I would guess. Right? And this is asking, is f differentiable on 3, 7? And the answer is yes, because there's no cusp or vertical tangent. And is f continuous? Yes, there's no whole jump or asymptote. And as we can see, since it's continuous and differentiable, there is a place on this graph that satisfies the mean value theorem, where the slope of the secant line is equal to the slope of the tangent line. However, what happens if those two conditions are not equal? So if we look at example 3 from this, and we draw the secant line from 1 to 5, we get this line. And if I try to find a tangent line that's parallel, I found that the point should be at this point. But there's a problem with this point because at this c value, f prime of c does not exist because there is a cusp, which means the derivative does not exist. And if I pick any other point on this graph, if I draw my tangent lines, they are never going to be parallel. So is g differentiable on 1, 5? The answer is no. Is it continuous? Yes. But there is no value at x equals c because at the value it should be, the function's not differentiable. So the derivative slope is undefined and does not equal the slope of the secant line. And that's why the function needs to be both continuous and differentiable. If we look at these three graphs, we can determine about if it matters if it is differentiable at the endpoint. So if we look at this first example, it says it differentiable on the open interval 1, 4, which means we do not care about what happens at x equals 4. So everywhere between 1 and 4, it is differentiable. And it is also continuous everywhere on 1, 4, and also at the endpoints. Now if I draw the secant line from 1 to 4, this would be my line. And if I draw another secant line and then drag it to see if I can find a parallel tangent, I find that about approximately there is a tangent line that has the same slope. So therefore it doesn't matter if it's differentiable at the endpoints because everywhere in between I can find the derivative, and which means that somewhere in that interval the derivative is going to equal the average rate of change. These two graphs we're going to use to explore is if it matters if it's continuous or not. So if we look at our first graph, if I look between 1 and let's pick 9, this point, and we draw the secant line, so this would be the secant line, and if I try to find if a tangent line is parallel, we can actually find a line that is parallel, or we can find a place where the slope of the tangent line is equal to the slope of the secant line. So for this example, it does work even though that condition failed. But if I look at the example number 2 and I look between 5 and 7, I can also draw my secant line here. And we can obviously tell that nowhere between 5 and 7, no matter where I draw my tangent line, it's never going to be parallel to this because this slope is negative and the slope between 5 and 7 is always positive. So here, the mean value theorem fails because h of x is not continuous. On 5, 7. And this is at the endpoint of this interval, and that's why the function needs to be continuous at the endpoints as well. But if I pick this function, we found that the mean value theorem does work even though the first hypothesis that the function is continuous is not satisfied. So sometimes the mean value theorem will work if the function is not continuous, but it's not guaranteed. And that's why we still need to check if the function is continuous, because if it is and it's differentiable, there has to be a c value that's true. But if it's not continuous, there could be a c value, but we're not 100% sure. And if you go through the worksheet that I gave you on Monday and try the different examples, that should show you all the different cases and the reason why the hypothesis can be true and why it may not be true, but the mean value still works. So problems that you're going to have to do is you're going to have to find the value of c algebraically that satisfies the mean value theorem. So algebraically, to find the value of c, we find the derivative and we set the derivative equal to the average rate of change for that interval. So here's an example. It says f of x equals x cubed on the interval 0, 4. Show that f of x satisfies the conditions of the mean value theorem, and then find the value of x equals c that makes the mean value theorem true. So the first thing we have to show is that f of x is continuous, and since f of x is a polynomial function, by definition of a polynomial function, f of x must be continuous. For actually all real numbers, but definitely on the interval 1, 4. Okay? And if we take the derivative, you get 3x squared. And again, 3x squared is a polynomial, which means f prime of x exists. Sorry, this should be 0, not 1, 4. F prime of x exists at every point on 0, 4. Again, because it's a polynomial function, which means there's no cusps or vertical tangents. Okay. So we showed that this function satisfies the two conditions of the mean value theorem. Then in order to find the value of c, we're going to find the average rate of change and set it equal to the instantaneous rate of change. So remember, the average rate of change is f of b, so b is 4 in this case, minus f of a, which a is 0, all over b minus a. And to find f of 4, we plug it into our calculator. So 4 cubed gives us 64. 0 cubed is 0, and I'm going to divide that by 4. And then 64 divided by 4 gives me 16. Okay? And this is our average rate of change. And the mean value theorem says the average rate of change has to be equal to the instantaneous rate of change. So the instantaneous rate of change is the derivative. So the derivative is 3x squared. We're looking for a specific value. So we can say that specific value is c. So if we let x equal c, we have 3c squared. And that has to equal the average rate of change by the mean value theorem. So this is the instantaneous rate of change, and this is the average rate of change. And we want to solve for the c value that makes it true. So I do c squared is equal to 16 over 3, and c is equal to the square root of 16 over 3, which is 4 over the square root of 3. And to find the exact value, we can put it in the calculator. And if you do that, we get 2.3094. Okay. So this is the value of c that makes the mean value theorem true. And this is how we solve a problem algebraically. One last problem that will be similar to one on your homework is this following problem. So it says, in the interval given, write an equation for the following: the secant line from the endpoints and the tangent line to f, in the interval that is parallel to the secant line. Okay. So in order to find the secant line, we need to use our equation for a secant line, which is f of b minus f of a all over b minus a. So our interval is 1 of 3, so this is a, this is b. We're going to find f of 3 minus f of 1 all over 3 minus 1. And so this is equal to f of 3, if I plug in here, is 3 minus 1, which is 2. And the square root of 2, we're just going to leave it for now as the square root of 2. Minus 1 minus 1 is 0, so the square root of 0, which is 0. And if I take 3 minus 1, I get 2. So the slope of the secant line slope is square root of 2 over 2. Now, this wants an equation for the following. So to write the equation, we can pick either 1 or 3 as our x value, and then find the corresponding y value, and write the equation in point-slope form. So for example, if I pick 1, I would do y minus 0, because that's the y value I found for 1, is equal to the square root of 2 over 2, and x minus 1. So this is the equation for the secant line. Then they want the equation for the tangent line that's parallel to the secant line. So in order to find that, I have to figure out the slope, which of course is going to be the same. So this is my tangent line. If we label it, this is my secant. We need to figure out where this occurs. So we need to find the c value that makes it true in order to find the point that's on the tangent line. So if I take my derivative, now remember we have to use the chain rule, and the exponent is 1/2 because it's the square root. So I bring down the exponent, leave the inside the same, subtract 1 from 1/2, which is negative 1/2, and the derivative of the inside is 1, so I don't need to write it. So this, if I rewrite this without the negative exponent, is 1 over 2, the square root of x minus 1. And this has to equal the square root of 2 over 2. So to find this, we can cross multiply. So I have 2 equals 2 the square root of 2 times the square root of x minus 1. I can divide by 2 on both sides. And then I just get, if I come over here, 1 equals the square root of 2 times the square root of x minus 1. And then we can divide by the square root of 2. So I get 1 over the square root of 2. Actually, let's make this a little bit easier. If we come back a step, we can actually square both sides. So if I square both sides, I get 1 is equal to 2, because I can square each one individually since I'm multiplying, times x minus 1. And this will make it easier to solve. So I get 1 is equal to 2x minus 2. And if I add 2, I get 3 equals 2x. So x equals 3 over 2. So that's the x coordinate on my point. I need to find the y coordinate. So to do that, I plug 3/2 into my original to find the y coordinate. So f of 3/2 is the square root of 3/2 minus 1. 3/2 minus 1, so this would be 2 over 2, which is the square root of 1/2. And then you can leave it like that because, again, in calculus we don't have to simplify. And then my tangent line, if we come over here, is y minus y1, which is the square root of 1/2, which if you want to make it in simplest radical form, you can, but you don't have to, is equal to the square root of 2 over 2 x minus 3/2. And you can graph it to make sure that at this point your line is parallel to the secant line in order to check it. And that is your lesson on the mean value theorem. Please now do page 206 on the calendar for day 6, which is the date of Wednesday, November 21st. Please have a nice Thanksgiving.